the red line, which has some oscillations which are related to the pole scale characteristic length, and then obviously an average signal. And so we want to replace that by the coupled problem with the average signal and the fluctuation. So typically, this looks interesting because here we see that we sort of recover some sort of oscillations, local periodicity of the system, which is an interesting thing. And if I do that, if I inject that decomposition here, I first get a very simple equation here, and another equation for the deviation. So we have a coupled problem here, and on the next slide I'll just go through the mathematics in a quite straightforward manner. So let us take the average of the balance equation. That's very important. Since everything is smooth here, this is simple. I have the divergence of the average, and if I introduce the decompositions, I get this macro scale or would-be macro scale equation in which I have the gradient of the average temperature, and here some term involving the deviation. So this is not yet in a closed form, and to get a closed form, I need the governing equation for the deviation. So the governing equation is just a small scale equation that I will write using the decomposition. So the pole scale equation is just that. And well, I am tempted to try to simplify that by using this equation. So if I subtract this equation to this one, I get an equation like that, which in the end gives a governing equation for the deviation. So I have a diffusion term here with the temperature deviation. I have an integral term here, and I have a source that depends on two things. It depends, of course, on the heterogeneities, the variations of the diffusion coefficients, and it depends on the large-scale gradient. So if I come back here, in places where there is no gradient, deviation is 0, and the fluctuation here is larger where I have a steep gradient. That's a very nice feature because I have a linear, I have two coupled equations with a linear here relationship term involving the temperature, the gradient of the average temperature. And this suggests to introduce some approximate solution of this coupled problem, and the approximated solution is actually what is called the closure. So the closure is not something that just pops up because I want to have a closure. The closure must be associated to the mathematical structure of the coupled problem that you are working on, and that's very important. And that's why linear problem, it looks easy. If it is nonlinear, this is a little bit more involved. I will not develop things today, but this can. So if I introduce a linear relationship, and then introduce that in the governing equation here, I get a governing equation for this mapping vector. And the governing equation is just a diffusion equation for this mapping vector, and a source term, which is the divergence of the fluctuation of the diffusivity. So what triggers some pulse media effect is just the fluctuation of the transport properties. This comes from the fact that the average of that is 0, and then Professor Pillai has added some additional things which are most of the time periodicity conditions, but I have a slide on to discuss that particular thing. Once I have got that, I can introduce that in the average of the pole scale equations, and I get the macro scale equation here, in which Kf is just the average of the diffusion tensor plus this correction term here that comes from the mapping between the temperature deviation and the gradient of the temperature. So that's something that will be repeated many times. It's simpler here because I have taken a smooth field K. It turns out that if you define all this in the sense of generalized function or distribution theory, it also works for a piecewise conductivity. But most people are not familiar with distribution theory, so I'm not going to use that here. And this is the way it can be used has been already illustrated by Professor Pirai. So you have to get some sort of data, X-ray topography, NMR, whatever. You solve for the mapping quantities, and you get what you want, your effective property. Well, it's not that straightforward. The use of periodicity condition is very powerful. Let us take an example. This unit cell looks bizarre, but actually this is a unit cell for a stratified medium. So all kind of geometrical orientations, anisotropy, etc., will be solved in a very straightforward manner if you have a periodic system. You don't mind about it. And if you introduce a unit cell like that in the closure problem, you will get your effective tensor, which is something a little bit complicated, but involving the vector orienting the stratified system. Well, so that looks very powerful. No problem with anisotropy. Well, but what if I have an image of a medium, a real medium, which is not necessarily periodic? There are many periodic systems. If you work, for instance, with structure packing in chemical engineering, they often are truly periodic systems. So they are periodic systems, but some are not periodic, and so there are many possibilities. One of the first ideas was, let us periodize that. Well, this may create problems. Let us take this, for instance, and I will make it periodic by just reproducing the image. And of course, I've chosen that to illustrate my stuff. And what I see here is that if I introduce periodicity, I create a bias here. I just block the flow, any flow in this direction. So there are problems if you want to apply without considering all the problems of periodicity anywhere. And this is one of the problems which is most of the time hidden in many packages you will find in commercial about calculating effective properties on X-ray images. So there is a lot of commercial stuff available, but people are not really giving all the information for people to be able to manipulate that. We won't problem.
If you make a large RAV by mirroring the images?
So there are many possibilities. I'm just this is actually this is still an open problem. So you may use some sort of effective theory. So you just make a larger system and just calculate the effective properties on inside that. There are still bias, or people are just reverting back to the original problem and introducing what is called permeameter conditions, either in a very simple case, but those boundary conditions do not handle properly anisotropy effects unless they are oriented along the axis or X or Y or Z. You can relax that by using what I call Baumberger condition, because one of the first papers using that was published by Baumberger, but it's called a linear permeameter. So you just impose boundary conditions here, which are, so this drawing should be on the right side here. So there are many things. You take time to develop all the possibilities, the advantages and drawbacks of things, but it's important to understand that this must be addressed, and do not use the things that are in the, I will not mention any code, but many software attached to image reconstruction. They do something which is not necessarily what you want to use for your particular system. So be careful about that. This is the message. The second message is, of course, about the side of the image you want to use. And that's a big problem because we have very accurate X-ray tomograph, but they don't make very big images. And that's an important concern, which is illustrated here in the case of randomly distributed diffusivity. And what I will look at, I will look at the size, the evolution of the effective conductivity in the x-axis direction versus the ratio of the side of the averaging volume with respect to some correlation length in the system. And there has been a lot of stuff trying to understand what's going on here. And in general, this is what happens. If I take several images, I can do some statistical analysis. So let us take a small volume. I will essentially have that gray figure here, large variance for the effective permeability calculated, and the expectation will be something like that. And what happens is that if I increase the ratio size of the volume versus the correlation length, then in general the variance decreases. And at the end, of course, the variance is so small that you only solve over one picture, and you are pretty sure that you have something which is representative of your medium. But this is not always the case when you use X-ray images, because most often we are somewhere in between here. So if you want to use your results, you have to work on the statistics of that. This is one important property for those upscaling problem, which I would like to mention. So now let us go to more complicated problem. The first one of interest is the transport of a chemical species, and I will do that only in this latest short lecture on the tracer case. But there are results available for more advanced problem, including, for instance, the use of Stefan Maxwell equations or things like that. So this is very simple, but the methodology can be applied to a more complicated system. So in that case, I have the Stokes equation, the total mass balance, and essentially that which is added to the problem discussed by Professor Pillay some time ago. So the advection diffusion equation and the particular boundary condition here. I will first start with passive, which is called passive dispersion. So the flux of the chemical species is zero at the interface between the beta phase and the sigma phase. And I will use that methodology, upscaling methodology, I just summarized before on the simple case. So first, let us do the averaging of the transport equation here. So I will use the averaging transport theorem for the divergence, for the gradient. I will introduce the deviations, and I will use the approximations which have been discussed before. And if you mix all that, you get the following results. So you get an accumulation term which is already under a closed form. This is typical here of problems. Remember that when we average, we have two possibilities. We have intrinsic average. So if there is a buildup of concentration, there will be accumulation because the concentration here changes. But that might be also an accumulation for the porous volume because of change in the porosity. So those dual effects are ubiquitous in all porous media physics. The averaging of that is split in two terms, and one which is a macro scale advection term, and then something here which in the end will produce a dispersion, the dispersion term in the final macroscale equation. Here I have something which is equivalent to what has been introduced by Professor Pillay for the pressure. So I have both this macroscale stuff plus this tortuosity term here. And so we need to determine, this has already been determined by Professor Pillay. So this is a given field in this particular case. because I made the assumption that I have a tracer, so density and viscosity do not change with the concentration. So this is a known field, and I have to determine this one and to be able to calculate that, and you calculate that. So the second step is to find the governing equation for that, and I'll just remind you that the governing equation is just the original power scale equation that I have tweaked a little bit. And to tweak that, I have used that decomposition, and also I will use that equation to simplify a little bit the equation. This is where the assumption of a local constant porosity take place. This modification is essentially straightforward if you assume that locally all gradients or time variation of porosity are small. So you can extract that and get a governing equation for the average concentration, and that will be useful to do that. Actually, I have not written the equation. There's well, I deleted too much slides apparently in the system.
Excuse me.
Yes.
The previous slide. Could you please go back to the previous slide?
Yes. Which one? This one?
Yeah. So the bottom equation, the second term, is it like?
The second term. Which one? This one?
Yeah. So that's being transported by superficial velocity.
You can. You have. Let me do that here. So you have to average that. You introduce whatever you want to introduce, but let us, for instance, introduce in which here this is the intrinsic velocity, and here the intrinsic concentration. If I do that, I have the average of U beta, C beta, of course, plus there will be cross averages, like for instance U beta, C beta theta, plus U beta theta, C beta, and then this final dispersion stuff. Here, let me remind that when I do that, I have somewhere here the phase indicator, because I'm working here with fields which are only defined in the beta phase. Okay, so that's the correct description. And if I take that using the approximation I have introduced before, I can extract that from the average. I get the average of gamma beta, which is epsilon beta. And I can write that under two forms. This one, or if I want, introduce the filtration velocity here. And the filtration velocity is actually that. So both, depending on what you are interested in, you may write that. That's a mathematics. So I have not written let me write the small scale equation. I took a lecture I made to von Karman, but I had many hours, so I probably deleted too many slides. So the let me use that notation for the intrinsic. It's much straightforward. Okay, so this is the pole scale equation. So I will subtract on that the macro scale, the average equation divided by epsilon beta, assuming that locally the porosity is not varying too much. Okay, so if I do that, I will essentially subtract something like that, which is this equation. I just rewrite that equation. So if I subtract that, I will get the governing equation here for the concentration deviation. With the important terms are those terms. So it's easy to do that from the world. Plus terms which are integrals, integral terms. This is the governing equation. So I will have essentially time variation of the deviation concentration. A source term here that depends on the fluctuation of velocity and the gradient of the average concentration. Something that will advect the term that affect the deviation concentration, and then diffusion that, and then additional terms which are of very slow varying properties. So the most important term in these equations are those. Now, there is also a boundary condition. Can I get rid of this at this time? You are okay with that? So I have the macro scale equation, which reads something like plus stuff. I have the micro scale, macro, and I have a boundary condition, which essentially gives the following. So now, two things. Those coupled equations are all time dependent. What is the characteristic time scale of this equation? This is something related to the diffusion coefficient d beta. So the characteristic time scales here is something which depends on the small scale and which depends on the micro scale, the free diffusion coefficient. What is the time scale here? Well, that's a little bit complicated. Of course, if I initially put just a spot of concentration, then the time scale and the length scale associated to C beta will be small. But this is not the kind of process I am interested in. I'm interested in, for instance, the behavior of a pollutant in a reservoir or in an aquifer. So I'm interested by scales which are much larger than the small L. So after a while, it's not that simple. It's something straightforward. The while here works because I'm working with a diffusion adduction equation, which is non-degenerate. So there is a. But it turns out that if you have diffusion adduction equation, there will be some smoothing, and in the end, this will have characteristic length scale which are much larger than L. So let us assume that. I should put here LC, but most of the time for simplification, we will assume that LC is actually the large scale of the system, and so characteristic time scale will be something like that. So far, I do not know that. If D star would be 3 order of magnitude, then I could not. So I'm stuck at this point because I don't have that particular characteristic time scale. But it turns out that most of the time, but I have to verify that, at the end of the process, at the end of the upscaling, I get something which is 1 order of magnitude. Maybe there are different cases, so I have to check that. But in most of the time, I can assume that the time scales are organized like that. So in that case, it's like when you solve an ODE system, if you have eigenvalues which are very, very different, the small eigenvalue, you just put 0 in your system, for instance. So I can solve a steady state equation here. It's not a steady state. It is still time dependent, but the time dependencies comes only from that. So in this coupling, I have the time evolution at the macro scale of the macro scale of the average concentration, and then I have a local steady state coupling that will essentially relate my deviation to the gradient of the concentration. Is that okay with you? That's important, and I will show later for heat transfer that this is not always the case. So I have to verify that this is correct for my application. But if I do, for instance, diffusion in a double porosity system, like in many catalytic beds, then there will be 2 time scales, one for the macro scale porosity and another one for the micro scale porosity in the beads. And there are many, many cases for which the time scale, there is a 2 order of magnitude difference between those two. And so if your packet bed is not big enough, there will be problems. So it's not always the case.
If not, if the time scale was not separated, would you end up with a sort of time convolution term?
That's in the next slide. So I will be back to that later. Okay, so now I have all that stuff done, and I can introduce a closure of the problem, and which takes into the advantage of the fact that I have a linear equations here. So the closure here is also the same that for the simple problem, and this equation which essentially leads to so the additional terms are discarded here, the integral terms are discarded, they don't play a major role. So I have a governing equation for this mapping vector with a source term that depends on the fluctuation of velocity and transport of B, and the boundary condition here with a source term that depends on the geometry of the system. Okay, this traditional standard condition, and plus I just put here periodicity condition, but remember that of course it must be discussed depending on the kind of material you are interested in. So that's the closure, and if you solve that, then you will be able to transform your average equation into, which is called a dispersion equation, in which I have this accumulation term we already discussed. I have this macro scale advection, where I could put epsilon u here with the intrinsic velocity, and this here I have effective diffusion, mathematically speaking, and this effective diffusion tensor actually is not purely diffusive. There is a diffusive part, which is the original diffusion coefficient corrected by a tortuosity term that depends on this dyadic n dot n tensorally multiplied by b. And I have this additional term here that depends on the fluctuation. So this is the structure, mathematical structure of the effective dispersion term here. I would like just to emphasize 2 things here. The macro scale flux is that part. So in the macro scale flux, there is a restriction due to the fact that we are working with a pulse medium, and there is also a restriction because our pulse medium is tortuous. That's very important. Many people, and often in many books, or things are written, you don't know what are the definitions. So I recommend to look at the way the equations are written to be sure that often people, they just write, they get rid of epsilon because they assume it's homogeneous, but you can do that, of course, but this part is not the macroscale flux. You have a, here if I have a fluid layer, the microscale flux is just a fixed law in that particular case. And here, the macroscale flux is minus epsilon times b. Do not forget that, because if you have a 10% porosity, for instance, you make 1 order of magnitude error, which is of course important. And just before lunch, I'd like to take advantage of that to show just some results which are classical. So this, in the diffusion case, this effective diffusion part versus the original molecular diffusion coefficient versus porosity, it looks like something like that. So it's not the straight line here. So there are some tortuosity effects, but tortuosity effects in this particular case are not very important. Often, let me say a word about tortuosity. The word tortuosity has been used in many. So tortuosity for me is just that. I have a diffusion coefficient which is d beta. And I may say that this is, so I will call that tortuosity. And tortuosity in that case comes from the solution of PDEs. Many people have tried to estimate that using geometrical consideration, things like that, and so there are many definitions of tortuosity. To me, it's just the way I write that, but the key is solving the PDEs for D. Question. So the overall macroscale flux is really something which has two effects. One is a decrease here. This is always below d beta, so tortuosity is always greater than 1. And also there is this restriction due to the fact that I'm working with closed medium, and so I have to take into account that in the system. So that's for diffusion, and for so that's classical stuff for most of you. And of course you have this dispersion curve, which is typical. So the Peclet number is some sort of reference velocity, reference characteristic length, and the diffusion coefficient. And if I plot the effective diffusion coefficient versus the molecular diffusion coefficient, I have this well-known curve that people use for many cases. So in general, I have for a low Peclet number a purely diffusive behavior with tortuosity effect below 1. Transition, which might be a problem because many, for instance, experimental devices you are here, so you have to take into account those nonlinearities. And then a regime, let us forget about that. But I have a dispersive regime which scales with the Peclet number to the power n, and maximum is equal to 2 in the case of a quasi-flow in a tube, which is called the Taylor-Harris theory. But in general, n is below 2, by the 1.8 something for arrays structure media, and then it goes to 1 if you have more and more randomness in the system. And many people in petroleum engineering or in the hydrology sciences, they use n equal to 1, which is correct or a crude approximation closer to 1.1 for a sun than 1. that's an approximation that simplifies the life in a great deal. And this is always a tensor because of this dispersion effect. And so the dispersion in the linear dispersion case, for instance, dispersion can be written under the form of something that takes into account the tortuosity effect, and then this kind of tensorial writing in which I have a longitudinal dispersivity and a transversal dispersivity, and if I look at that, it gives the following picture for the dispersion curves. So I have the dispersion curve for the longitudinal dispersion in the direction of the flow, and in the transversal direction I have something like that, with here almost 1 order of magnitude difference. So that's very, very important. The dispersion effects are very, very important for closed media physics because it creates some anisotropy in the system, which in many cases, especially in the codes for petroleum engineering and hydrology, are essentially taken into account under this form. So what do you think? We stopped here? So
Take a break.
Yeah. Just something, I have to leave at 3 sharp, so because I have a plane late afternoon. So if someone wants to discuss with me, and